Okay. Hello, everybody. I'm Guangyuan Ma from the Institute of Information Engineering, Chinese Academy of Sciences. And today I will give a lecture about our new pre-training schema for dense retrieval. So first, let's give an overview of pre-training for dense retrieval and our DPR, dense passage retrieval. Pre-training is a is a popular technology for DPR, and it usually takes mask autoencoder architecture, which is MAE for short. And dense retrieval benefits from these MAE-style pre-training architectures. And it composed of an encoder and a decoder. The encoder is just the full-sized pre-training language models. It comprises the textual inputs and encode as sentence representations. And the decoder, they are usually just limited transformer blocks, only one layer or two layers. And their role is to decode or reconstruct the input signals and boosting the encoder representations, such as the CLS representations, where the gradient flow from the decoder to the encoder. And there are three trees for the MRE pre-training. The first one is a systematic structure. I just introduced the encoder is full size and the decoder is very shallow. And the second one is bottlenecked connections. And its meaning is that the encoder and the decoder, they are connected only where the CLS representations. And the third one is a virus of reconstruction signals. And they are the key innovation of the MAE pre-training for DPR. And they are specially designed pretext. And I can conclude three categories of reconstruction signals, and there are more decoding tasks. They are including the autoencoding, autoregression, or the enhanced decoding, and I will introduce to you guys later. And here's the background for the DPR. The similarity search, and as you know, the encoder will produce representations and query representations and passage representations, computing similarity with the dot product or the cosine similarity. And typically, if the encoder is a bird, and we can pull in the representations from the CLS position, and I will mark the hidden states the last hidden states at the CLS token position as its representations. And I will mark it as H last CLS. And for MAE pre-training, the encoder part is just a normal mask language model pre-training loss. And detailedly, it will, if you input a mask, if you input a text T, and first we will mask it with a proportion of mask ratio, and we forward it with the encoder, and we will compute the MLM loss with the cross entropy. And the decoder part, there are three categories, as I mentioned before. And the first one is auto-encoding decoder. What's the design? The first one shares the same input as the encoder, but the decoder will have a higher mask ratio. And this is to increase the difficulty for the decoder learning. And for the loss, they are just a normal mask language model loss with cross entropy to predict all the mask positions. And for autoregression decoder, the inputs are different. They are normal mask, and the decoder, they will use casual language model loss. That's also a generative loss, just as the GPT does. And the third one is a rising star for the MAE pre-training. And is widely used in the retro MAE or the BGE model developed by BAI. And what's the design of enhanced decoding decoder? Concretely, it's a cross attention pattern with an extreme max ratio. And they claim this will improve the token usage. So as for models, it's just a single transformer layers. It's a transformer. It will have Q, K, and V, query key values as the key components. And as for query part, it is composed of CRS representation plus the position embedding of each position. And this sum up will act as the query. And as for key and the values, they just use the input embeddings as the key and values. If you get Q, K, and V, then they will do a transformers cross attention and the feed-forward network and the post-layer norm. So that's what the model is doing. And the second key innovation design for enhanced decoding decoder is the positional specific attention mask. So suppose we have a mask and it's L plus L, and L is the sequence length. So there are two rules. The first one is masking diagonal, and the second one is just the random sampling from each line of the position. And to note that this implementation for this mask sampling task takes power of 2 data processing complexity. So it's really computational expensive for CPU. And as for the loss, it's just a normal cross-entropy loss to predict all input tokens. So let's allow for the memory pre-training for DPR. So what's the drawbacks of the existing pre-training technology of the MAE? I will give 3 points. The first one is lack of interpretability. So we just don't know why these designs are working, and their lack of underlying reasons. And the second one is it will introduce additional complexity, such as power of 2 data processing or the additional GPU computation time. And the third one is just you add a decoder. It will use extra GPU memories. And so here's the questions. What's the factor contributes to the performance gains for ME pre-training? And the second one is how to develop an interpretable pre-training schema for DPR. And the third one is, could we design a pre-training schema with less extra complexity? So let's go in with these questions. So the first one, we will make some preliminary studies. So what factors contribute to the performance gains for MAE? So I can give you 2 tables, and there are 5 experiments. The first one is we just use the original BERT checkpoint. And the further pre-train, the second one, further pre-train is just removing the decoder from the ME style pre-training, and meanwhile keeping other hyperparameters or settings just the same as the last 3 ME pre-training, and the auto-encoding, auto-regression, and enhanced decoding. So there are 5 experiments. So let's look at these 2 tables. I just tested the performance on MS macro datasets and natural questions and trivial QA. And I also evaluate their pre-training losses, which is evil MLM losses. And typically, if you have a lower pre-training loss, and it will perform better. And you can check it with the downstream retrieval performances. So the first conclusion is that both further pre-training and MAE pre-training will contribute to the downstream retrieval performance. And among these designs, the enhanced decoding achieves the best. And as you can see, the MS macro, the NQ, and the trivial QA is performing the best. And but for the evaluation MRM loss, the pre-training loss are not the key factors influencing the downstream retrieval performances because for the pre-train, this design, it has the lowest evil MRM loss, but its performance is below the enhanced decoding. So, how to develop an integrable pre-training schema? If we want to take a look at what is happening in the MAE pre-training of the DPR, so the first thought is to visualize it. And we can just project the CLS representations to the vocabulary dimension and see what is happening at each token position and what the logits or the frequency is changing. So as the pipeline, if we have an input and it will be forwarded with the encoder, and we will get representations, and we will just project these representations to the vocabulary dimension, and I will check the top K logits. Logits will be viewed as the frequency, and if lists such as A token appears in the input, and I will give a check. And if it is not in the input, I will give a cross. So as we can see from the visualizations and the input token coverage, which we plot from the top 20 to the top 140. So as we can see, enhanced decoding, it has the highest input token coverage. So if we project the enhanced decoding to the vocabulary dimension, and it will share the highest top K logits with its original input. This is just it's fine. And if we can see, if we can develop a pre-training schema with less complexity, so I will just drop the decoder. So building upon the above observations about token compositions and these downstream performances, and we will propose a schema which removes the decoder in the MAE pre-training. So just use a prediction task will work the best. And as the former says, I project the CLS representations to the vocabulary space, and then we will use a cross-entropy to predict the token bag or the bag of words of all input tokens. And here's the decoding prediction loss. And so the final loss will be the encoder master language model loss and the decoder bag of word loss. So here's the results. And as you can see, our pre-training schema bag of word prediction, which removes the decoder, and it performs the best on the 3 downstream data sets. And our pre-training task is extremely computational efficient, and it has the minor training speed degeneration, as you see. And the enhanced decoding, it has over 60% training speed degeneration. And here's the ablation studies. And as you can see, our bag of word prediction loss achieves the best on all negative settings compared to other MAE pre-training. So here's also ablation on the Bayer benchmarks, which is a zero-shot benchmarks. And we can see that if the encoder-mask ratio is 15%, it performs the best. And if we remove the bag of word prediction, and the performance will degenerate. So the input token coverage, our bag of prediction has the highest input token coverage, which is considered contribute to the downstream retrieval performances. So that's the summary. So just use backward prediction loss instead of MAE encoder-decoder loss. So thank you very much.